This video is going to go into more detail on our diagnostic measures. So I'm going to talk about leverage and Cook's distance and try to give you some intuition behind them, as well as the mathematical justification for these measures. Let me mention that I'm going to do a bit of math, and so that math is really intended for the students who are interested in becoming data scientists. If you're not interested in becoming the data scientist, but you're just a little more interested in having a high level understanding of these statistics, you can skip over the two or 3 minutes of this video that will have all the math in it. All right, so I've summarized the key results of linear regression. So let me start with concise statement of the model. So here is our model. We've assumed that y's are just some linear transformation of the x's plus some errors. These errors have two assumed properties. One is they have mean zero. And so because the errors have to have, the errors of the residuals are going to have mean zero, that's why I've been telling you your residual plot should be centered at the zero line. So half the residuals, if they're normally distributed, should be above the line. Half the residuals should be below the line. So the residual plot is going to allow us to check this first assumption. The second assumption is that the errors have constant variance. So what this statement means is it's a very concise way to say that all of my errors are independent of one another, well, uncorrelated with each other, and they have the same variance. So let me just go over to the document camera and show you exactly what I mean by this. So I have the variance of an error matrix has to equal sigma squared. Maybe I move the camera a little bit and then you don't get as much shadow from me. Sigma squared times I. So the way to think about this is I have the variance of some errors. So let's just say I had 3 errors. So E3, that's a vector. And what I'm saying is this has to equal sigma squared times the identity matrix, which looks like this. All right, so it's a sigma squared there. So the variance of this first error is equal to sigma squared. The variance of the second error is sigma squared. The variance of the third error is sigma squared. Now the covariance between any two errors is going to be 0. And so that's why all of these zeros imply uncorrelated errors. I'm going to make my document camera a little bit bigger so that you can see the writing there. All right, good. Now, what we found is that my OLS estimates equal this very famous expression. So this is the set of OLS estimates, and this is the way we estimate our error variance. So the mean squared error estimates this sigma squared, so this S squared thing is estimating that. Now, a couple key results for us are that my y hat is, well, let's just go write this out. It's kind of almost fun to write it out. So what are my y hats? So the y hats will be x times my slope estimates, which equal, well, x times, what is this b? Well, this b is x transpose x inverse times x transpose times y. Now, this quantity right here is a very famous matrix that we call the H matrix or the hat matrix. And the reason we call it the hat matrix is because when you multiply y by the hat matrix, it puts a hat on the y. So this is called our hat matrix. So it's really important to note that y hat is just h times y. Now, another key property is that my errors, which are equal to, well, what are my errors? It's just y minus y hat. So this is going to be y. And what is y hat? Well, it's just x times b. So that's another important result to have. Now we can go off and compute the variance of these two random variables, so y hat and e hat. So what is the variance of y hat? Well, this is just going to be the variance of h times y. Now this is, think of this as a matrix constant, and it's actually a symmetric matrix. So this is symmetrical. All right, so H transpose is the same as H. That's what I mean by symmetric. Well, my Y is a random variable. So remember, if you have what is the variance of some constant A times a random variable X? Well, this is A squared times the variance of X. We have the same thing when we have a matrix constant, except that we multiply this. We have to pre and post multiply that, and since H transpose is just the same as H, this is going to be H times the variance of Y times H again. So what is this? This is going to be H times sigma squared I times H again. Well, the sigma squared is just a scalar value, so we can pull that out in front, and we're left with sigma squared times h. Now the identity matrix doesn't change anything. That's like multiplying by a 1. So it's really sigma squared hh, but hh is just h. So sigma squared times h is the variance of y hat. Now why did we do this? Well, let's just go check it. So let's just say we're going to check h times h is equal to h. This is called an idempotent matrix. When you multiply it by itself, you get the original thing back. So let's go check that out. So h times h is just, what is my h matrix? Here it is. So x times x transpose x inverse x transpose, so that's my H matrix, and just put another copy of that. Well, x times x transpose x inverse x transpose, but notice I have x transpose x inverse times x transpose x, so this whole thing is the identity, and it's like sticking a 1 in the middle. And so what are we left with? Well, we were left with x times x transpose x inverse x transpose, but that's just h, right? So that's why that h times itself is just h. Well, what is the variance of my residuals? So the variance of my residuals is going to be the variance of y minus, we forgot the variance sign, y minus y hat. So there's a detail that these have to be independent of one another, and I'm not going to establish that. It's because this is perpendicular to this, but let's not, that's a property from least squares. I can distribute this because they're independent of one another. So this is going to be y minus the variance of y hat. All right, so what do we have here? This is sigma squared times I. So where's that coming from? Somewhere up here, I assume that, right here. And then what was this? This is minus sigma squared times h. And so we're left with sigma squared times I minus h. Now, this is really important unless this thing is a bunch of constants, my E hats will not have constant variance. So even if my original E's have constant variance, my estimated residuals will not. So note, estimated residuals, so E hat, have non-constant variance. So when I look at my residual plot, the residual plot could show that I don't have constant variance, even though my original residuals had constant variance. And so that's a bit of a problem. So the remedy that we're going to have for this is to standardize our estimated residuals by dividing by the standard deviations, to take the square root of these values. And that's going to be called a standardized residual, and it avoids this potential problem. Now in practice, the non-constant variance caused by this is usually not enough to worry about, and that's why R still gives you the unstandardized residuals first. Keep it simple. The third residual plot that it shows you has these adjusted standardized residuals that take care of that. All right, back to my course packet. So definition, the leverage of an observation is going to be the diagonal entry for that observation in the hat matrix. Now these hat diagonal hat entries, or leverage values, have some properties that can be established. They're always between 0 and 1, and they sum to the number of predictors in your model. So I want to start by giving us a little bit of intuition, mathematical intuition, behind why we care about these diagonal entries. So let's go back to my document camera for a second. And I want to refresh your memory that, well, this result that we had up here. So y hat is just h times y. That's an equal sign. I didn't mean to put a dot above it. So it's this hat matrix that puts the hat on y hat. So let's write this out for a second. What is y hat? Well, I really have, say, a y hat 1, a y hat 2, and y hat 3. So let's just say my n is 3 to keep my life really simple here. What does the hat matrix look like? Well, we're going to have h11, h12, h13. Then we could write it all out if we like. These two have to equal each other. h22, h23, and then let's finish it. h31, h32, h33 times y1, y2, y3. Now, I'm not going to write out the entire vector, but let's just write out the first row, and I think we'll see it from the first row. So what is the first row? It's going to be this times this, plus this times this, plus this times this. So h11y1 plus h12y2 plus h13y3, and we are going to have something similar here and something similar here. So let's just really put a microscope on this expression. So h11 is telling us how much influence does the y1 value have on my predicted value of y1. Okay, so the bigger this number, the more influence that y1 is going to have when I compute the predicted value y hat 1. So I hope you see that from the arithmetic that I've just written out. Likewise, the size of y22 is going to be how much influence y2 has on the y hat 2 value. So that's why we focus on these hat matrix diagonal elements to understand this leverage. Now there's a famous result that you'll find in many basic undergraduate statistics books when they cover simple linear regression. And so we have this expression right here. So let's go over to my document camera again. And so HII, let me just write it out for us, is this. X sub I minus X bar squared divided by the sum of these Xi's minus X bar squared values. Now the interesting piece of this is the Xi minus X bar. So this is just a constant that is the same for all observations. This value is what changes. So let's say I've got a simple linear regression. Here's X, here's Y. And I've got a bunch of values here. So, all right. Somewhere here is the mean of X. So that's my X bar. What is X bar? So what is Xi minus X bar squared? Well, this is simply the squared distance from the mean. So if I had an X that was exactly the mean, well, I would have that X minus the mean. This would be 0, and that observation would have comparatively small leverage. So if it were exactly 0, the leverage would just be 1 over n. Alternatively, if I have points out here, so points out here or points out here would have high leverage. So I find the distance from the center, and it's large, therefore they would have high leverage. So a point out here, if it's, let's say I've got an extra X out here, that point is outside the swarm, and it can exert a lot of leverage because it's so far from the mean. If I had a point that was equally far from the scatter, but in the middle, it wouldn't exert much leverage. It would have to pull the whole line down, whereas this point would take a line that looks like this and flip it to, pull it down, if you will. It's going to pull it down because it has leverage, whereas this point might just move the whole line down a whisker because it's in the middle. It doesn't have any leverage. So that's what we mean by leverage. All right, so a few more things. I already mentioned problem 1. So problem 1, the estimated residuals do not have constant variance, even when the model, which assumes homoscedastic errors, is true. So that's what I've already derived when we found this variance on paper. Okay, so how do we handle that? Well, we standardize them. So I'm going to divide by 1 minus the leverage. Where is that coming from? Well, that's 1 minus the leverage right there. So that's I'm standardizing the residual. So sometimes these are called studentized residuals, sometimes they're called internal standardized residuals. There's a lot of names for it. And so when we generate the diagnostics in R, the third diagnostic shows us the standardized residuals. Now there's another problem that we have, and the problem is if there are outliers, our estimate of the standard error gets inflated, and this just deflates all of our residuals. So we do something that hints at a very important technique that we're going to have coming up soon, which is to try estimating the model without that observation. So I'm going to say, Y hat sub parentheses I, that notation right there, indicates the y hats I get if I've omitted an observation from the estimation. And then this is the corresponding corresponding error. And we can go off and compute our deleted residuals or studentized deleted external residuals. There's lots of names for these. The last thing that I want to mention with this, though, is Cook's distance. And so Cook's distance is perhaps the most important diagnostic that we have that uses these y hat values predicted without an observation. So to illustrate all of this, I'm going to go over to my scratch pad for a second and just draw a picture for you. So let's say that I had a simple linear regression, and maybe my x's look something like this. All right, so I got all these x's down here, and let's say further that I've got an x up here. So I have one more x that is way up there, and that is meant to be an outlier. So I'm going to call this observation I. So let's say that's our observation I. If I were to fit a regression line using all my data, the regression line would look something like this. Okay, this value, which is far from the mean of x, would exert a lot of leverage, and it would just pull the whole line up. And I'll use red to indicate the regression that I would get without that observation. So if I deleted that case from my data, I would get a regression line that looks something like this. So I'm just going to say that this is y hat as a vector with I omitted. So all of these predicted values would be what I would get having deleted I. This would be the y hats using all of my data. Okay, I'd get the blue line. Now let's remember what our Cook's distance formula was. So Cook's distance, which I have to go look this up. Cook's distance is d sub I. So how much influence does this observation have? Well, the formula I had was this. We're going to make a sum. J equals 1 to n. I need a different index, so we'll call it j. And I'm just going to take my y hat value minus the other y hat value. So I might as well write that in red to be consistent. This is going to be y hat sub j parentheses I. And let's go square that, and this all gets divided by some constant. So all we're saying with Cook's distance is how much do all of the y hat values change if I get rid of one observation? And so in this case, my y hats change a lot because these two lines are very different. So when this is my my observation, di is big. Now let's just go draw ourselves another plot. So I'm going to try to have the same scatter plot here, and then we've got that outlier up here. But I'm going to make a different observation, my observation I. So let's say this observation right here is observation I. So what is my estimated regression equation, including that observation? And the answer is it would look something like this. So again, that value up here is going to yank the line up. But if I were to delete this case, what would happen to my regression line? The answer is not much. So maybe this is my regression line dropping observation I. So this would be my y hat sub I versus the blue one is my y hat line. So here, d sub I is small. Why? because these two lines are almost on top of each other. Therefore, the difference between them is almost always 0, and therefore those observations are very small. So let's go back to the course packet for a second. And I tried to work through an example. There was a problem that I'd given you way back during the review of simple linear regression. I called it the machine example. And I changed one of the observations here so that it would be an outlier that would be influential. And that shows up here where my my Cook's distance plot shows a value that has a Cook's distance near 1. And so that would be labeled as an influential case. So actually, this example is where I've modified it to make it even more influential so that it's beyond 1. So in general, when you are looking at a Cook's distance plot, values that are out on, this is a contour map, the values beyond 1 are deemed influential and you want to pay attention to those. Values between 0.5 and 1 are close to being influential and you probably want to pay attention to those. Anything in this trough between 0.5, the 0.5 bands, we don't worry about much with a Cook's distance plot because we don't see them as being influential. Okay, that's it for my my lecture on leverage and Cook's distance.